This is section 5.1, finding the general area underneath a curve using the rectangle method. You divide the interval from 0 to 2 into n, the number of rectangles.
Our first graph is y equals x squared, and our first subinterval is n equals 4, meaning that we divide the interval of 0 to 2 into 4 rectangles.
As you can see, there is extra area above the curve, so this is not an exact measurement. We are finding the area underneath the curve using 4 rectangles. We will use the sum sequence method, which adds all of the rectangles underneath of a curve to get a more exact value of area. There are 6 different blanks. The first blank in the sum sequence formula is the function. In this case, it is x squared.
The second blank represents your variable, so in this case it would be x.
The next blank is a plus b over n. The interval in which you are working is a comma b. So in this case, a is 0, and b over n would be 2 over 4. 0 plus 2 over 4 is 0.5, so the third blank is 0.5. The fourth blank is b, or 2. The fourth blank is b. The fifth blank is b over n, which is 2 over 4, or 0.5 again. You end the parentheses and multiply by b over n, again 0.5. We are finding the area underneath the curve using the sum sequence method using 4 rectangles. In the sum sequence method, there are 6 blanks. The first blank is the function, in this case x squared. Next is the variable x. The third blank is a plus b over n. Our interval is 0 to 2, or a to b. So a is 0 plus 2 over 4, which is 0.5. Your next blank is b, or 2. The next blank is again b over n, or 2 over 4, which equals 0.5. You end the parentheses and multiply by b over n, which is 0.5 again.
Now it's time to move to the calculator to finish the problem. To get sum sequence, you go to second stat, go over to math, and number 5 would be sum. Then you hit second stat again, go to ops, and number 5 is sequence. Now it's time to plug in all your numbers. First number is x squared, then you put a comma. Next is x, comma, 0.5, comma, 2, comma, 0.5 again. You have to end your double parentheses, and then you multiply all of that times 0.5. Your answer comes out to 3.75, and it's area, so it's units squared. Our next subinterval is n over 50, so it's using 50 rectangles in that interval to find the area.
Using the sum sequence n equals 50, you write sum sequence x squared comma x, comma 0.04, comma 2, comma 0.04, close parentheses, times 0.04.
We go back to our calculator and do the same thing that we've been doing before, find the sum sequence, plug in your numbers, just like we did before, with your commas in between. Close your brackets, times 0.04, and our answer comes out to 2.7472 units squared. The next example is the same as the one we just did, except the equation changes from y equals 3 over x plus 2, and our interval changes from 0 to 1.
Instead of using the rectangle method, which is great for approximating the area under a curve, but it's not that exact, we are going straight to the sum sequence method. The first blank is your function, or 3 over x plus 2. Next blank is a plus b over n.
Next blank is your variable,
That's
which
right.
is x,
Right.
Your
Then the
next-
next blank is a plus b over n.
which is 0.1.
The next blank is then b, or the end of your variable, or of your interval, which is 1. The next blank is b over n, or 0.1. You end parentheses and multiply by b over n again, or 0.1.
You can plug all this into your calculator like we just showed, and your answer should come out to 1.192 units squared. We can move on to our second n value, which is 50. So we find the area of the 50 rectangles using sum sequence again.
You start with your function 3 over x plus 2. Next is your variable, or x. Then is a plus b over n, or 0 plus 0.02. You then plug in b, or 1. Then b over n, or 0.02. You close parentheses and multiply by b over n, or 0.02.
After you plug all this into your calculator, you should get 1.211 units squared. Then it's on to our last n value, which is 100. So we're finding the area of the 100 rectangles under the curve.
Use the sum sequence method and start with your function again, 3 over x plus 2. Next is your variable x. Then a plus b over n, or 0.01. Then b, which is 1, 0.1, or b over n, times b over n,
which is 0.1. Your answer should come out to 1.214 units squared.
We are moving into finding an area under a curve using the antiderivative method. An antiderivative is a function in which its derivative is the original function.
In this example, we need to find the area between the graph of f of x equals 1/2 x plus 1 on the interval of a to x, which will be -2 to some random x value that you pick on the bottom. If you shade in the region that interval represents, it's a basic triangle. So we can use a basic area formula for a triangle to figure out the area underneath the curve. That formula would be 1/2 base times the height. So in this problem, the area would equal 1/2. The base number would be x, and then this is 2, so it'd be x plus 2. The height is from here to here, which is the function, so it'd be the straight function, which is 1/2 x plus 1. After we distribute, it equals 1/2 x squared plus 2x plus 2. If you distribute a little more, the area function is 1 divided by 4 x squared plus x plus 1. Then we need to find the derivative of that function. So you multiply the 2 times the 1/4 to get 1/2 x. And then your constant in front of the x is 1, so it's plus 1. What's weird is this, the antiderivative, equals the function that we tried to find the area under in the first place.
Continuing to use the antiderivative method, we will show that the area underneath the curve of the function f of x equals 4 is 4.
We can draw the simple graph of f of x equals 4, which would be like this. Your interval is a to x, which they're giving us is 3, and some random x value farther down. If you close off the boundary, it's a rectangle, so we can use the simple area of a rectangle formula to figure out the area underneath the curve. That would be the base times the height. In this problem, the base would be x minus the 3, and your height would simply be the function, which is 4. When you distribute, you get that a sub x equals 4x minus 12. That would be the area underneath the curve. You need to find the derivative of that, which would equal 4, which is exactly like the original function f of x equals 4.
thus proving the antiderivative.
Our last and final example is estimating the area between the graph of sine of x and the interval of 0 to pi over 2.
We can use the sum sequence method when using the rectangle method. When n equals 10, or the number of rectangles underneath the curve is 10, you write sum sequence times the function, or sine of x, comma the variable, x. Next is a plus b over n,
Which is pi over 20,
then the end of the interval, or b,
which is pi over 2,
and then b over n,
which is pi over 20 again,
close the parentheses, times b over n.
which is pi over 20. When you plug all of that into your calculator, you should get 1.076 units squared. Now we have to find the area under the curve using 50 subintervals.
You again use the sum sequence method using sine of x, comma, a plus b over n,
Just pi over 100,
comma, the end of the interval, still pi over 2, then b over n,
which is pi over 100 again,
closing the parentheses and again multiplying by b over n.
just pi over 100 yet again. After you're plugging this into your calculator, you should get 1.016 units squared. Last, we need to find the area beneath the graph using 100 subintervals.
Using subsequence one more time, you use the curve sine of x, comma the variable x. You then use a plus b over n
Which is pi over 200,
times the end of the interval, again pi over 2, times b over n,
which is pi over 200,
closing parentheses and multiplying by b over n.
which is pi over 200 again. After plugging this into your calculator, you should get 1.008 units squared.